Good afternoon, everyone. So, who are the presenters today? Any presenters? All right. It seems a bit of low number of students. So it's good to go for the quiz now. So I have very few questions prepared time back actually to give for we discussed right for a random quiz all of a sudden. I think it's a nice day, just four students in the class. So we'll go for that 10 percentage quiz too quickly. Yes, the quiz is, the question is very easy question. Yes, the question is you have to write a small description or a small note on virtual memory. You have 5 minutes to write. Once you complete it, you can drop an email to me. Now its time is 1:33, 1:38. We'll complete the assignment. It's 10 percentage valid. I have changed it to 5 marks, guys. We'll do it two assignments, in-class assignments. So it's just 5 marks because it's very limited time. Uh, and some of you are joining using a mobile phone. So I have reduced the All right, thank you. You can drop an email to me and stop writing the stuff. I'm not expecting very detailed answer, just very high level. It's just a very small answer. But in any case, if you have used ChatGPT or any other tool for generating content, you will entitle for 0 marks. Right, guys. Thank you. You can drop an email. Don't write a lot. It's much easy for me to write bullet points if you can. The most important points only. But paragraphs are okay. Uh, just 5 points is more than enough. Right, right. I will give 2 minutes to submit your answers. No, it's 1:39, 1:41 around. We'll see. We'll complete the acceptance of these answers. Meanwhile, any presenters today?
Yes, sir.
Right, then we can start. Make sure to add your index number uh, whenever you are dropping an email. It's much easy for me. Please make sure to drop with your index number. Right, we can start the presentations then. Meanwhile, others can submit. I will give around 1 minute further for the submissions. I'm not expecting guys a lot. I'm expecting very small amount of details. In very high level, it's more than enough. Right. Well, your camera. Right. Good. We can continue there. You have muted. You have muted.
Oh, oh, sorry, sir. Sorry.
Right. Now it's good.
Continue,
Go ahead.
continue. Okay. Good evening, guys. Today we are going to discuss a very important topic. It's about Boolean algebra and truth tables. So I think that this is a very easy topic for all of you guys because you guys have already studied this topic in your A levels. So before moving to our presentation, I would like to introduce my group members. I'm Sandini and my other group member is Rashmi. So let's move on to our presentation. So today in our presentation, we are going to briefly talk about Boolean algebra, truth tables, how construct a truth table, how get a Boolean expression from a truth table, SOP expressions and POS expressions, logical operations in truth tables, basic laws of algebra, importance of truth tables, and we are going to discuss some practical questions based on this theory. So next slide. In here, we are going to talk about Boolean algebra. So Boolean algebra is a branch of mathematics that deals with operations on logical values with binary variables. So in truth tables also, we use Boolean variables that are represented with binary numbers 1 and 0. So normally we represent truth value with 1 and the false value with 0. So now we are going to discuss about the history of Boolean algebra. So in 1854, logical algebra was published by George Boole 5. Today it known as Boolean algebra. And in 1938, Claude Shannon, he was the first person who applied Boole's theories to design a logical circuit. So from now on, I will hand over this presentation to Rashmi.
Yeah, what has happened? Something has gone wrong, guys. Is that only for me? Or can you hear anything? I can't see anything. What has happened?
Excuse me,
Representatives.
sir, can you give us a 10 minute, 2 minutes? We just having a technical issue.
All right, all right. No worries, no worries.
Sorry for the delay, sir. Can we continue it now?
Sure, please continue. Yeah, continue, please.
Sir, still we are having that technical problem. So can we give this chance to another group? We will do it in last. I'm really sorry.
Right.
Signal dropping. Right.
All right. The next team. Next team, there's a small issue with some of your colleagues. So what we can do, any voluntary team is willing to do the work, continue to another assignment, another presentation. Sanjana, what we can do? Sanjana, right? Grammar testing. I can't remember the boy's name.
Can you start group 10, guys?
For the group 10 members, group 10, we have started to tables flip-flops. Tarusha, Tishadi, and Oneli. Tarusha, are you there? No.
So what about group 11? Shall we start?
Group,
11.
are you ready to do?
Yeah, we are ready.
Sure, we'll go ahead.
Okay. Sonali, you may start.
So, good evening, everyone. After that technical error, I would love to start a presentation with a fun fact. So, have you guys ever wondered what the first mouse looked like and what material was used to create it? And as you can see in our second slide, it was made from wood. And this is what it looked like. And you guys may wonder why I mentioned the first mouse that was made from wood. It is because our topic for today is input and output techniques, where we mainly discuss what is an I/O subsystem, I/O device and its I/O techniques and its types, and also the emerging trends of I/O systems. Guys, the table of content may seem so simple, but there are some interesting and important subtopics that I, Sonali, and my other colleagues, Nishani and Filmini, will be explained further. So, first of all, we will be talking about the I/O subsystem. What is a subsystem means? It is a system that is a part of larger system. And here, I/O subsystem is a part of the operating system that manages the flow of information between the I/O device and the computer, which is more like the bridge between those two. And now you guys can see the graphical representation of I/O subsystem. So I/O device plays a main role in this I/O subsystem topic, right? I think I/O devices are not a new topic for you all, but the I/O device classification may seem new. Just to remind the concept of I/O device, there is a small activity. So over here, there are 8 pictures. 5 of them are I/O devices and 3 of them are irrelevant. So the 5 of those devices are monitor, printer, speaker, microphone, and keyboard and mouse. So actually what is an I/O device means? Imagine the computer as a busy king who perform tasks and process information. And now imagine I/O device as a messenger of the country who delivers messages to and from the king, which is the computer. So that is the I/O device. As I told you earlier, let's get into the more interesting part, which is the I/O device classification. So there are 3 criteria that I/O devices can be classified. They are based on the type of the devices interact with, based on the direction of data flow, and the last one is based on the mode of operation. The first criteria can be categorized into 3 parts as human readable, machine readable, and communication devices. So these human readable devices are mostly suitable to interact with liveware. And the machine readable devices are appropriate to exchange data with electronic devices. And the last one is communication devices, which is acceptable to transfer data over network. So the second criteria, which is based on the direction of data flow. This criteria is easy for me to explain using an example. So think you are typing something using a keyboard in a Word document, and you are using a printer to print that document. Here, keyboard is the input device where we input some data, and the printer is the output device, which we got the printed document as the output. And there are some devices like touch screens and disk drives, which they are acting both as input and output devices. So the third criteria, which is based on the mode of operation. There are 2 types as block devices and character devices. Those block devices are handled in chunks, and you can read, write, and move those entire block at once. But character devices are completely opposite for block devices. They act as individuals and flow in and out one by one. I think every part of computer system has its own importance. So we will talk about these importance now. So you can see it enables user interaction and also facilitate communication with other devices and store or retrieve data while optimizing data transfer. So in order to fulfill the functions and importances, the IO system must be efficient and effective. As we said, this is a subsystem and therefore it must be designed in a such way to achieve its efficiency and effectiveness. Now let's focus on what are those challenges and goals in designing IO system. The goals of IO system design to ensure the fast, efficient, and reliable data transfer and standardized interfaces and handle devices effectively. It is all about the challenges and goals, guys. I would like to pass my presentation over to Nishani to start off the core of our presentation, IO techniques. Thank you.
Thank you, Sonali. Hello, everyone, and hope everyone is doing fine. So, to talk about IO techniques, I would like to consider a scenario, and I want everyone to join with me in that. So, imagine you're a chef in a restaurant. You have to prepare various dishes for your customers using different ingredients and tools. You also have to communicate with your staff, such as the waiters and assistant chefs. So, how do you manage all these tasks efficiently and effectively? Now compare this situation to a computer system. Now you need to focus in this part, or else later you might wonder why she's talking about a kitchen in an IT presentation. So y'all better focus. So when you compare the scenario for a computer system, you're like the CPU, the central processing unit that controls the execution of tasks and programs. The ingredients and tools are like the IO devices, while the staff are like the interface units or the hardware components that connect the CPU and the devices. Then what about the dishes? The dishes are like the data and the information that is transferred between the CPU and the devices. Now, how do you coordinate your activities with the devices and interface units? You need to maintain a proper communication, and this is where IO techniques come into action. So, IO techniques are different methods for transferring data between the CPU and the IO devices to operate in a synchronized manner, allowing for efficient data exchange. When it comes to IO techniques, there are three types. We speak of the programmed IO, interrupt-driven IO, and DMA or direct memory access. The first one, programmed IO. So in programmed IO, it's more like following a recipe step by step. You have to check each ingredient and tool before you use it and wait for it to be ready. So just imagine you're going to bake something. So you'll be checking if the oven is preheated or not. You also have to wait for each operation to finish. So you won't be doing anything else while you're waiting. So that means the programmed IO is really simple, but really inefficient. Now this is simple means while carrying out a single task, you don't need to worry about the others. So you means what? The CPU. You just have to follow the instructions and wait for the results. It is inefficient because you waste a lot of time waiting for the ingredients and tools to be ready. You could be doing other things while you're waiting, such as preparing another dish maybe, but you won't. So that means till the IO devices are getting ready, the CPU is capable of carrying out some other tasks, but it won't. It will wait until the data transfers of the IO devices are completed. Therefore, this involves a lot of CPU overhead and will be inefficient for high-speed data transfers. So in programmed IO, we use a special method to communicate with IO devices and see whether they are ready or not. So that method we call polling. This is like asking your staff to report to you every time when they have something ready for you. Now I use the word report but not notify, right? So I'm highlighting this part. So reporting, that means imagine you ask the waiter to tell you when a customer places an order. Since you said to report, you need to check with them periodically to see if they're ready with something, which means the CPU needs to repeatedly check whether the IO devices are ready or not. So this is called polling. Now polling is not very optimal. Now why it's not very optimal? Because you have to check with the staff frequently. That means the CPU needs to check with the interface units repeatedly whether the IO devices are ready or not. Now this is really annoying, right? It sounds annoying and it is really annoying and distracting for both the CPU and for the IO interface units. So because of this checking, there is a possibility to miss out some important events if you don't check often enough. So polling has its own advantages like simplicity, but has a numerous disadvantages like it wastes the time and slow down the overall system since it checks each and every device at a time, right? In a fixed order it checks. Has the risk of missing signals from certain devices and creating delays on devices that need urgent attention. So there are numerous drawbacks in this polling method. Programmed I/O can be divided into two. So those are shared I/O and memory mapped I/O. Now this classification is based upon a fact. That is, this classification is based on the way in which the memory access the I/O devices. So based on the way in which the processor access the I/O devices, programmed I/O can be categorized into two, shared I/O and memory mapped I/O. So we'll move to shared I/O. In shared I/O, from the word itself, it's like sharing, right? So when we go back for the restaurant scenario, it's like sharing the same ingredients and tools with assistant chefs. So that means, for example, you and another chef might use the same oven, mixer, knife, whatever, right? So you need to coordinate with them to avoid any conflicts and errors. So you have to agree on who uses what and when. So there won't be any overlapping or errors. So in shared I/O, a separate set of addresses are assigned to the I/O devices. Therefore, a special set of I/O instructions and commands are necessary to access the I/O devices. So this method is really helpful in maximizing the utilization of resources. You don't have to maintain multiple devices for each and every process, but you can also utilize the devices that are not in use by others. However, shared I/O has some challenges and risks. Now, challenge is why? Because it needs to synchronize and communicate with other processors to avoid interference and confusion. So you have to deal with certain delays as devices compete for access. As I said, in shared I/O, the same chefs will be sharing the same ingredients, right? So these devices will be shared among processors. So there will be a competition for the access. Then it has a risk because you might lose data or quality of the devices since maybe they won't be reliable or not be compatible. So we are done with shared I/O and we'll be moving for memory mapped I/O. In memory mapped I/O, it's like assigning a specific location in your kitchen for each and every ingredient and tool. Now, why the kitchen, I said? It's because that means the I/O devices will be assigned a set of addresses from the memory address space itself. So in shared I/O, they assign a separate set of addresses. But in memory mapped I/O, they'll be utilizing the same address space of the main memory for the I/O devices. Therefore, there won't be any requirement to maintain any special I/O commands or instructions to access the devices, but the same read or write instructions of the main memory will be used to access the I/O devices too. So memory mapped I/O is really convenient and fast for accessing devices. Now, why this is convenient? Because you don't have to have any special instructions or commands to access the devices. It is fast because you don't have to go through the interface units or the CPU to access the devices, but can access it directly from the main memory. However, this memory mapped I/O has some limitations and drawbacks. Limitations because it reduces the available memory space for storing data and programs, because you need to reserve some memory locations for the I/O devices and that cannot be used for anything else. In this method, there might be conflicts and errors if the main memory itself will be used. Therefore, these I/O devices even need to be compatible with the memory itself. So there might be any differences of the requirements, such as maybe the speeds might differ, the formats or the sizes. So there might be different compatible issues between those two. Then
Excuse
we are
me.
moving for simple pros and cons of
Yeah,
the both shared I/O and memory mapped I/O. In shared I/O,
excuse
there are two
me.
address spaces separately for memory and
Excuse
I/O.
me.
Sorry, yeah, yes, sir.
The screen is a bit zoom out, so can you please a little bit shrink it? It's too much
I think it's
zoomed
because there's this pen over here.
because for some reason it's like full.
Let me check it, sir. Give me a minute.
Sure. Right now it's okay. Thanks.
Is it? It's fine.
Yeah,
It's
yeah.
fine,
Now
right?
it's good now. All right.
Okay. Yeah. So, okay. Yeah, the pros and cons, right? So in shared IO, there were two different address spaces for the memory and for the IO devices. But the drawback is that it needs to maintain a special IO instructions to access the IO devices. Then back again for memory mapped IO, it will be using the same address space as of the main memory. So there won't be any requirement of any special IO commands, but we'll be using the same read or write instructions, but has a limitation of reduction in the available memory address space. Then this will be the most simplest summary of both shared IO and memory mapped IO, right? Two separate address spaces, it will be having the same address space. Then it will have a need for special IO commands, but the memory map won't have because it will be use the same read or write instructions. Then we are moving for the second technique. So we are done with programmed IO, right? So programmed IO got categorized into two, shared IO and memory mapped. Then we are moving for the second, and that is interrupt-driven IO. So interrupt-driven IO is like having your staff to notify you when they have something ready for you. Now, previously I said to report, right? Over there, I didn't use the word notify. Over here, I'm using the word notify. So notify means, for example, in the restaurant scenario, back to it, the waiter might ring a bell when a customer places an order. So as the chef, you need to stop what you are doing and attend to them when they notify you. So that means in interrupt-driven IO, it is really efficient and responsive than programmed IO. It is more efficient because you don't have to waste time checking or waiting for the devices to be ready. You can do the other things until they notify you they are ready with something. It is more responsive because you can react to the devices as soon as they are ready. You don't have to delay or have the risk of missing any events. However, interrupt-driven IO requires some a more requirement for hardware and software support. So this is because the hardware support is to generate and handle the interrupt signals from the devices. Now interrupts are what? The notifications, right? So it requires software support to save and restore the state of the CPU and the program when an interrupt occurs. So interrupt-driven IO requires a mechanism to prioritize and resolve multiple interrupts from different devices, because you might get different interrupts from different devices at the same time simultaneously. So you need to have a special mechanism in order to prioritize such interrupts. So at that, we'll be talking about the interrupt service routine. So handling interrupts and servicing IO requests. Now this is more like the restaurant has turned busy, right? It has gone for a busy version. So you will have to deal with different customers and staff who need the attention and service. So you have to make sure that you will be balancing your time as well as your resources as well as satisfy everyone. So when a customer places an order, the waiter notifies you by ringing a bell, right? Now, what does that mean? This notification or this ringing bell means it's more like an interrupt signal from an IO device to the CPU. Then what does the CPU do? So as the chef point of view, you need to stop what you're doing and take the order. So this is like saving the state of the CPU and the program, right? Then you'll be writing down what is there in the order and you hand it over to an assistant chef. So that means it's like service in the IO request. So you look into what is there in the interrupt and you assign it for another one, right? To carry it out. So that is like service in the IO request. Then you resume what you were doing before. So that is like restoring the state of the CPU and the program. So sometimes, now since I said it is a busy restaurant, you might have multiple customers or staff who need your attention at the same time. So just imagine 2 or 3 waiters might ring the bell at the same time. So that is like what? It's like having multiple interrupt signals from different devices. So you need to decide which notifying or which ringing bell you need to attend first. So that means you need to prioritize and resolve the interrupts. So for like to prioritize and resolve the interrupts, you need to have some criteria. You can't just choose, okay, I'll randomly choose this and pay attention for that. No, you need to use some criteria. So over there, you might use, I mean, you means what? The CPU, right? So the CPU will be using criteria like the urgency or the importance or maybe the order arrival of the request and also certain rules. You all might have heard these rules in previous ones, I guess, because those are first come, first serve, round robin, or priority queue. Such stuff will be used to prioritize and resolve the interrupts. So we are done with interrupt-driven I/O. That means we are done with two techniques, programmed I/O and interrupt-driven I/O. Let's compare the differences between the programmed I/O and the interrupt-driven I/O. So in programmed I/O, what does the CPU do? It initiates the data transfer and wait till it is done by polling its status register in a loop. But in interrupt-driven, CPU initiates the data transfer and resumes its normal execution without waiting till the data transfer is completed. Then the CPU cannot perform any other task until the data transfer is completed in the programmed I/O. But in interrupt-driven, what does it do? It performs the data transfer and sends an interrupt signal to the CPU when it is done. So it makes sure CPU won't just stay idle looking for it, but it will carry out other tasks. Then in programmed I/O, it's really simple but really inefficient because it wastes the CPU time. On the other hand, in interrupt-driven, it's really efficient but complex. Complex because simultaneously it needs to attend for different interrupts. So it needs to have an interrupt handling mechanism and a special coordination between the CPU and the device. So we are done with the two techniques. Then we'll be moving for buffering for I/O performance. And for that, I cordially invite Sanali to carry out the presentation.
Thank you, Nishani, for that excellent explanation. So buffering. Some of you may have heard this word in A levels when discussing about cache memory, where the cache memory acts as a buffer to retrieve data from computer. And some ordinary people like me may have heard this word in TV commercials like the Airtel advertisement. So they are talking about the buffering speed. I'm sure that you all may have experienced this concept unintentionally when you streams a movie on an online platform where you press play, the video doesn't start playing immediately. It takes few seconds to buffer. During this buffering phase, the video player collects chunk of data and stores in a buffer. This buffer acts as a temporary storage area while ensuring the continuous flow of data to a device. While you watch the movie, like while you continue watching the movie, the buffer continues to fill up of the playback where it creates a reserve of data. And there is another familiar example for the vehicle lovers, where there is a vehicle part called buffer in vehicles, which provides a safety cushion and it allows smooth and controlled driving experience. There are three types of buffering techniques. The first one is single buffering, the other one is double buffering, and the last and most efficient one is circular buffering. So what is the single buffering means? It is a temporary storage area that holds the data before it is processed. It is just like a conveyor belt in a factory, where each item arrives, waits for its turn, and is processed further. However, this mechanism may lead to synchronization issues, where the CPU and I/O device operates at different speeds. So the other type of buffering technique is double buffering, where there are two buffers And the first one is for reading and displaying data. The other one is for writing and updating data. While one buffer is being filled, the other one is being emptied to provide a smooth and uninterrupted updates in computer graphics. So the last and most efficient type is circular buffering. It is, as the word says, it is like a never-ending cycle where data keeps moving in a continuous loop. So there are no any, it minimizes the interruptions when you are dealing with those computer graphics. So we can conclude that circular buffering is the most effective type of buffering technique. And that is all about this interesting concept. And I would love to pass my presentation to Pumini to discuss about the last and most important IO technique. Over to you, Pumini.
Thank you, Sonali. Now we talk about the direct memory access. If you know that all the programs in a computer perform using a CPU, that means any of operations that can't be possible without the CPU. If we consider the input-output devices, then think we have a input-output devices. We have a CPU and also we have a main memory. First, input-output devices transfer the data to CPU. Then CPU transfer the data to main memory. If we consider that all process, we can get 2 cycles. If involve the CPU for IO operations, that will take a lot of time because IO devices are slow, so can't match up with CPU speed. Therefore, CPU need to wait. That's a problem. What is the answer for this question? We can introduce a technique. That name is direct memory access. DMA can transfer the data between IO devices and main memory without involving the CPU. This technique is more efficient than programmed IO and interrupt-driven IO. This process managed by a chip as known as a DMA controller. It gets 4 parameters. There are source address, destination address, byte count, read or write. Then this is the diagram of DMA controller. DMA controller has 4 channels that can be used over 4 IO devices. Each channel consists of a 16-bit address and 14-bit counters. It communicates with the CPU through the data bus and control lines. The CPU can read and write into the DMA registers under the program control. The DMA controller then take over the system bus and transfer the data directly between the memory and IO devices. The CPU notified when the transfer is completed by an interrupt signal from the DMA controller. This picture of a DMA controller. This is a hardware. As I said, DMA controller is a chip and this is what it looks like. Now we will talk about what are functionalities of DMA controller. Main function is we can transfer the data between memory and IO devices without involving the CPU. Reduce the CPU overhead because DMA speed ups the memory operations by passing the involvement of the CPU. Communicate with the CPU, the memory, and the IO devices via data and control channels. Now, impact on DMA to CPU utilization. DMA controllers have a positive impact on CPU utilization. They reduce CPU overhead, enhance CPU availability and efficiency, ultimately leading to improved system performance. While they consume system resources and bandwidth, proper resource management and ensure optimized data transfer within the system. Then, DMA and its benefits for I/O performance. DMA is a technique that has transforms how data moves within the computer, reducing CPU overhead and enabling multitasking. It relies on communication channels called data and control channels to interact with the CPU, memory, and I/O devices, enabling them to exchange information and instructions. DMA is a superhero of data transfer, relieves the CPU from the tedious task of data movement and enables multitasking by allowing the CPU to focus on other tasks while data transfers are in progress. Through its communicate channels, DMA bridges the gap between the CPU, memory, and I/O devices, ensuring efficient collaboration. As we are done with the I/O techniques, let's see importance of I/O operations for computer system. I/O operations are essential for computer systems as they allow users to interact with the system, enable access to external data, facilitate parallel processing, and support various devices and applications. They form the backbone of communication and data transfer, making computers powerful tools for productivity, creativity, and connectivity in our digital world. Presently, the world is advancing with the help of AI. We can see that the technology is affecting almost every aspect of everything. Similarly, the I/O module is even advancing day by day with the such technology. Now let's see such advancements. Emerging trends and technologies. The current advancement in the input-output devices related to storage devices is the hybrid silicon laser. It is the product that is developed and recently demonstrated by the company Intel. Recent advancements in I/O technology. There are two. Non-volatile memory express for high-speed storage devices and remote direct memory access for efficient network I/O. First one is non-volatile memory express is a high-speed storage device that optimizes the performance of SSDs, reducing latency and maximizing throughput, making it ideal for quick and efficient storage access. Second one, remote direct memory access. It allows direct data transfers between remote systems memory without involving the CPU, resulting in low latency and reduced overhead. This improves network effectiveness and accelerates data transfers, making it beneficial for high performance computing, big data processing, and cloud computing applications. Thank you, guys.
Thank you, Piyumani. And with that, we come to the end of our presentation. So we discussed the 3 I/O techniques: programmed, interrupt-driven, and DMA or direct memory access, and the latest trends of the I/O. So it's time for the questions. Are there any questions? No, right?
All right,
Done.
it seems no questions from the audience. It's very good presentation, very clear, detailed, and informative. Good, good effort. Yeah, thank you. Yes, next presenters. The technical issue is fixed at the moment, or what's going on? Is that okay? Solved?
Yes, sir. Now we can do presentation.
You can do the presentations? Good. All right, go ahead.
So, can you all hear me?
Yeah, we can.
Okay, okay. Good evening, guys. Today we are going to discuss a very important topic. It's about Boolean algebra and truth tables.
Excuse
So,
me.
okay, sir. Yeah.
Not sure the screen is from one and sound is from someone. What's happened?
Oh, yes, sir. Because I can't turn on the camera on my laptop.
Oh,
So
okay.
if I can I turn off my camera?
Turn.
Yeah. Turn off my camera in my phone.
Well, if it is inconvenient nowadays, if you can, that's good. Whatever you decide, that's up to you.
Okay, so okay. So good evening, guys. Today we are going to discuss a very important topic. It's about Boolean algebra and truth tables. So this is really easy topic because you have already studied this lesson in your A levels. So before we are moving to our presentation, I would like to introduce my group members. I'm Sandini and my other group members are group member is Rashmi. So let's move on to our presentation. In today's presentation, we are going to mainly focus on Boolean algebra, truth tables, how construct a truth table, how get a Boolean expression from a truth table, SOP expression, POS expressions, and logical operations in truth tables, basic laws of algebra, importance of truth tables, and some practical questions based on this theory. So first, we are going to talk about Boolean algebra. So Boolean algebra is a branch of mathematics that deals with operations on logical values. So in the truth tables also, we represent truth table values with Boolean variables that are represented with binary numbers 1 and 0. So normally we represent truth value with 1 and the false value with 0. So now we are going to talk about the history of Boolean algebra. In 1854, logical algebra was published by George Boole 5. It today known as the Boolean algebra. And 1938, Claude Shannon was the first person who applied this Boole's work to design a logical circuit. So from now on, I will hand over this presentation to Rashmi.
Thank you, Sandini. So let me explain. Thank you, Sandini. So let me explain what is a truth table. A truth table is a visual representation that shows the relationship between input values and their corresponding output values in logic or digital circuit. So let's see how to construct a truth table. Next slide. In a truth table, there are rows and columns. A truth table consists of columns for input variable and an output variable. For example, input variable A, B, and the output variable is A and B. Let's see how to construct columns in rows in a truth table. Each row in the truth table represents a specific combination of input and show the resulting output value. To find the number of rows used in a truth table, take the number 2 raised to the power of the number of variables. For example, If there were two statements, it would be 2 to the power 2. That means there are 4 rows. For example, let's consider a truth table for logical AND operator. We have two input variables P and Q, and the truth table shows all the possible combination of zeros and ones for P and Q. There are two variables, so there is 4 rows because 2 to the power 2 is 4. There are 3 columns, one column for P input variable, one column for Q input variable, and other column for P and Q. Each row in the truth table represents a specific combination of P and Q. In this truth table, when both P and Q are 1, the output is 1. For all other combination, the output is 0. Now Sandini will explain how to get a Boolean expression from a truth table. Sandini?
Okay, thank you, Rashmi. Thank you, Rashmi. Now I'm going to talk about how to get a Boolean expression from a truth.
It's stuck. It's stuck for some reason. Is that for me or the presenter's side? Other members, please check what was happened to her. I think it's stuck for everyone, isn't it? Guys, can you hear? I can't hear anything. Is that my issue?
No, sir, it seems to be stuck for everyone, I think, yeah.
Sorry?
It seems to be stuck for everyone, sir.
Stuck for everyone, right? Okay. So group members, please inform her there is an issue.
So can you give us a minute? Let's fix this and count fastly.
All right, now it is. Yeah, I think what we can do for your team, shall we do it next week in a physical mode? I think the technical issue persists and it's a bit lagging for the entire flow because I think others also waiting. We have very limited time and it's a bit getting. What about
Sorry,
your idea?
sorry,
Yeah.
sir. Can we do last in today? There are another group. There's another group.
Yeah, well, or else you're Rashmi, isn't it?
Yes, sir.
Yeah, or else Rashmi, shall we do it next week? I'm okay with that. Huh?
Okay, sir.
Okay,
Sorry,
we'll do
sir.
it next week. Sometimes the network strengths are not good in some areas. I know
So
that.
yes,
Yeah,
in
no
here
worries.
it's raining heavily.
Yeah, might be. So no worries. We'll do it next week. I can understand. So empathically, I can
Thank you.
give a release for you. That's fine. I'm totally okay. So next week, please ready and come. Then we'll do the presentation in the class. Okay.
Thank you.
All right. Next group. I'm sorry. Next group. All of a sudden, it's coming to your head. Who is the next team that doing presentation today?
It's us, sir. We'll start our
Yes.
presentation. Hope it's
All
audible.
right. Yeah, it's audible.
Thank you, sir.
I can see 3 index numbers in one place.
We are all together, sir.
All together
In
in
the
a
same
one place. Interesting.
Yeah, sir.
Good. Interesting. All right, then we'll continue.
Yes, sir. We can- Guys, can you see my screen?
Yep, we can see.
Okay, thank you. So we are group 16 and today we are gonna present flip-flops. So as you know, I'm from an NIT background, okay? So whenever these guys told me flip-flops, like flip-flop slippers, what came up to my mind was the normal slippers which we wore daily. But here it's not the case. So what are flip-flops really in the computing world? So guys, we know the bits, that is the smallest unit that the computer can process and store. So flip-flops is like the storage component of this bit. So each and every flip-flop can store up to 1 bit, that is either a 0 or 1. So the main function of the flip-flop is to store the binary information. So moving on to the content, we would be firstly introducing and giving the basic idea about the flip-flops, and then moving on to the applications, and then we are having flip-flops, and we will be going on through the circuit diagrams, truth tables, and also the future developments of the flip-flops. Moving on, the introduction. So the flip-flops was evolved from the concept of latches. So flip-flops is like the updated version of latches. So it's like the fundamental building block of the circuit diagram. So we can normally present it using the circuit diagrams. So we are gonna explore different types of flip-flops and their applications in the further slides. So I told you all that the flip-flops are an updated version of the latches. So what is the difference between this latch and the flip-flop? So guys, you know, both of them have inputs, but in the latches, your inputs can be changed either intentionally or unintentionally. But if you get a flip-flop, those inputs are triggered by the clock signals. Like in the latches, if you change your inputs, intentionally or unintentionally maybe, like if you do it unintentionally, whatever the stored data will be destroyed. So it was like a disadvantage of the latches, and in order to overcome the disadvantage, they invented these flip-flops where you cannot straight away go and change the inputs. Instead, you have to change the clock, so that by changing the clock only you can change the inputs. So basically, it's like an updated version of the latches. Moving on, how actually the flip-flops are made. So if you get practically, if you get a flip-flop and see, they are made up of transistors. But in order to study theoretically, like if we are going to study, we are going to study by combining logic gates and making the circuit diagrams. So according to different types of inputs, like we can have 2 to 3 inputs, and how they change the state, we are going to classify the flip-flops as four according to the slide shown here. So we have the SR flip-flop, D flip-flop, JK, and T. Moving on. So as if you can remember the presentation which we did last, which the other groups did last year, last week, regarding the gates, the main gates which is used in the flip-flops are NAND and the NOR gate. So I'm gonna give you guys a brief description so that you'll get a good understanding. So NAND is like the combination of the NOR gate and the AND gate. So similarly, the NOR is the combination of the NOT and the OR gate. So as an example, if we have 0 and 0, according to the AND gate, your output would be 0. So according to the NAND gate, it would be the complement, which is 1. If you go to the NOR gate, it is the combination of NOT and OR. So 0 and 0 as the input, your output would be under the OR gate, it would be 0. And in the NOR gate, it would be the complement of the OR gate, which is 1. So similarly, it is going like that. So what you have to keep in mind is like whenever you get a 0 in the NAND gate, your output would be coming as 1. So what you have to keep in mind, it is whenever you get a 0 on your input, your output would be 1. In the NOR gate, it's the opposite of that. If you get any sort of 1 here in the inputs, your output's gonna be 0. So that point you have to keep in mind for your, so that it would be easy to get the whatever it is in the future slides. So aren't you all like curious in knowing the applications of the flip-flops in the real world? So Tharisha is gonna explain you. Over to Tharisha.
All right, so applications of flip-flops. So flip-flops are mainly used to store data. So the main function of flip-flops is to store data, and they are used to transfer data. They are also used in sequential logic circuits and in register circuits, and also in counters. So we will show you how each of these happen. So data storage. Data storage is the primary function of a flip-flop. So a flip-flop can store one bit at a time, and they are connected in a series and parallel manner. So mainly registers use flip-flops to store data. So this diagram shown here, it has 4 flip-flops, which means so each flip-flop can store one bit at a time. So this means that this diagram can store 4 bits at a time. So let's do one exercise. So how many flip-flops can you see in this list? Please, somebody can somebody tell me?
Eight.
Yeah. Yeah. So as you can see, this there are 8 flip-flops. So each flip-flop can store 1 bit. So whole flip-flop can store 8 bits. So moving on, flip-flops are also used to transfer data. So mainly, they are it is done by the clock signal. The clock signal initiates the flip-flop, but the clock signal can only store data temporarily. Um, it is used as the memory of the flip-flop. Because of the clock signal, inputs will not be changed intentionally. So multiplication and division methods are used for between JK and D flip-flops. Moving on, they are also used in sequential logic circuits. So flip-flops are the basic chips in sequential logic circuits. They are used as memory elements. So they are mainly used in, when it comes to sequential logic circuits, they are mainly used in clock sequential logic circuits because of the clock signals. So registers. Registers are made from a group of flip-flops. So the basic function of registers
Excuse me,
are
dear.
the
Excuse me.
yes.
Yeah, please switch off your camera because your network strength is not too good. So what you can do is switch off your camera, then the problem will resolve up to some extent.
Okay.
Switch off your camera.
So yeah, registers. So registers are made of a group of flip-flops. So the main function is to hold information within a digital system during a process. So some examples for registers are frequency registers, shift registers, and counters. Counter is a register that goes through a predetermined sequence of steps. It is not just a normal register. So the primary function of the counter is to produce a specified output pattern sequence. So now this is the interesting part. So we talked about the theoretical part of flip-flops. So now we will move to the diagrams. So I will hand over the presentation to Oneli to teach you guys about the SR ledgers.
Um, my camera because it's hard to explain, but hope it's okay for y'all. If it's like too, just let me know so that I can off my camera.
Yeah, switch off your camera. Then we can save the network stream.
But sir, it's like we were like prepared to draw the flip flop on the board and explain the circuit
Okay,
on
okay,
the board.
okay.
So,
Okay, now it is then. Now it is. We'll give a try.
sorry. Okay, thank you. So, sort of latch, if you remember the difference between the latch and the flip flop, right? So I told you the flip flop is an updated version of the latch. So these latches also can be prepared by using the NAND gate as well as the NOR gate. So these are the diagrams. So I'll be going through the NAND gate now. So here we have the two NAND gates here. This input with the set input and with the reset input. So of one this gate and off gate would be going on as an input. I'm gonna show you how this values come and how the output comes. So when you have 0, can you guys see? Here we have 0, and remember, like whenever we have 0 passing through the NAND gate, the output would be 1. And this one will add to this gate. So 1 NAND gate, you will get the output of 0. So Q I got as 1 and Q bar I have 0. So the combination which I explained you is this combination where S is 0, R is 1, and this is the set condition which I proved you. And now I'm gonna change my 0 to 1 and my 1 to 0. Now we'll see what happens. So always what you have to keep in mind is that you have to start the input which has 0. So always 0 passing from the NAND gate, it would result 1. So this one would be coming on as an input to this gate as 1 here. So 1 and 1 passing from the NAND gate, it would result 0. So whenever you have 1 and 0 as 0, your output would be 0 and Q bar would be 1. That was this combination which I showed you guys. Telling y'all, whenever you get 1 and 1 as the input, I'm gonna prove you that this flip-flop keeps the previous state, whatever the previous state. Now the previous state is 0 and 1 which came up. So they're going to keep it in mind and get back the previous state to your present condition. So I'll keep the previous state like this. Okay. Now here 1 coming up here, it would be 1 and 1 going through the NAND gate, it would be 0. And 0 again coming up for this NAND gate as an input to here, 1 and 0, again you will have 0. So you can, so 1 and 0, you will have 1. So you can see the previous, it has exactly come as 0 and 1 in the present state also. So whenever you have 1 and 1, they are going to keep the previous state in mind, and it's called the memory state, where you get the same output as the previous state. And then 0 and 0. Next, 0 and 0. So 0, whenever you have a 0 as an input passing on with the NAND gate, you will be getting 1. And here also 0 passing on, you will get 1. So guys, only Q and Q bar is our output. So like the complement of Q. So can this happen like 1 and 1 is not the complement of 1. So if it is 1 here, 0 has to be the output under this Q bar. So now there is a problem here. So this whenever you have 0, we call it as the invalid state because it does not come properly. So here you have 1 and 1, which is also called the invalid state. So 1 and 1 is the 1 and 1 is the memory state. 0 and 0 it's the invalid state. Then now I did this from the NAND gate. I've done from the NAND gate, and we have next from the NOR gate. So here we have the 2 NOR gates here. So these are the 2 NOR gates. We have the reset input and the set input. So in parallel to the reset, we have Q as the output. And and in parallel to S, we have Q bar as the output. So Tarusha will be telling you further on the NOR gates. Tarusha, over to you.
All right, so I will show you guys how the SR latch using the NOR gate works. So let's first take the second row. So let's start with the second row. So input for S is 0, input for R is 1. So as we know, whenever the input of NOR gate is 1, the output is 0. And 0, when it comes to this input, this becomes 1. So as shown here, the reset becomes 0 and 1. And likewise, when the S is 1 and R is 0, this becomes 0. And the input here becomes 0 and the output becomes 1. So Q becomes 1 and Q bar becomes 0. That is the set state. So I'll show you guys the memory state. So in previous latch using NAND gate, the memory state was both S and R being both inputs being 1. So in the NOR gate, in the SR latch using NOR gate, for the memory state, both inputs have to be 0. So I'll show you guys. So the previous output was Q1 and Q bar 0. So I'll prove it to you guys that the memory state gives the same output. So whenever the input of this is a NOR gate is 0, the output becomes 1. So this 1 becomes the input of the next gate. So here it becomes 0. Whenever the input of a NOR gate is 1, the output becomes 0. So we can see it gives us the same output as the previous values. So and now we have the not defined state. So So when both the inputs become 1, so let's take first start. So when the input is 1, this becomes 0. When it comes here, we have 1 here in the S. So when 1 goes to a NOR gate, it becomes 0. So as we can see, the both Q and Q bar has become 0. So it is the not defined state. Both Q and Q bar can't become 0. So now we are gonna move on to the flip-flop diagram. So this is not hard, but you better listen, because if you miss some parts, you won't understand. It will be hard for you to understand. So, and we will be asking questions from each flip-flop. So you guys better listen. So, and
Excuse me.
yeah.
Excuse me. Whenever the best student who answered, we can give a gift, right?
Yes, of course.
All right, guys, there is a one question after each and every slide. So prepare for the answers. What we can do, we'll give some points. What if?
Yeah.
Yeah. All right, guys, we'll go for what kind of a mechanism that we can go for? We can ask raise hands. All right.
Yeah.
Great.
Yeah.
All right, guys, you have nice opportunity to grab additional points. So there are some questions that they have prepared from after each and every slide, right? So if you know the answer, you can raise your hand. And what's your name, Puta?
I'm Tarusha.
Tarusha, you can pick the student that you want to ask the question.
Okay,
All
so
right.
no, sir. Okay, sir. Teshadi will move on from here. She will explain the flip-flop, so she will be asking the questions also.
All right, Tishadi.
Yeah, Teshadi.
All right, Tishadi, then it's up to you.
Okay, sir. So now I'll hand over the presentation to Teshadi.
Okay, guys, moving on to flip-flops. As Tharushan already explained, I guess you can have a basic knowledge about the basics of the flip-flops. So now we are moving on to what is actually a flip-flop. So under this, we are going to discuss the first flip-flop, that is SR flip-flop. This is the most common flip-flop that is used among all, and this is the simplest form of flip-flop. But every flip-flop has a limitation, so there will be some improvements and new names for different kind of flip-flops. So as you can see, the SR flip-flop is made of 2 NAND gates first. Then again, you can see the SR latch after this 2 NAND gates. So I'll be explaining the truth table and how this works. Okay, so as you can see, from there onwards, you can see the SR latch. So this works as same as the SR latch, only this part is the new thing that you're going to learn. Okay, so the only thing that has been changed is the clock. We are given a clock because we are given the clock as a control input, because then we don't want our input to change accidentally or intentionally. So here, first I'll give clock as 0. So I'll just draw the truth table here. Clock SR, and I'll just name these things SR, S star, and R star just for the explanation. but there are no some such thing as S star and R star. So when the clock is 0, any input that is going to the NAND gate, if the clock is 0, it should be 1. So S star becomes 1. I hope you can see the last thing. So I hope you can see this. So if the S star is 1 as 1, it comes as memory. And we can say that whenever the clock is low, it's going to be.
Can you
1
please take
and
it
1.
a bit up?
Yeah,
A bit, a bit to you, a bit to you, not outside, inside. You're taking outside, inside. Ah, right. A bit more, a bit more, a bit more. No, dear, no. Left. Ah, right. Nice. Now it's good. Nice position. All right.
So as you can see, when 1 and 1 comes as S star and R star, according to SR latch, it comes as memory. So I'm going to give you a point. That is, whenever the clock is low, we are going to store what is being there as the output. So once the clock is 1, that means clock is high only, we are changing the outputs. So this is what I was saying, that the clock is used for the control of inputs. That means whenever we can keep the clock low if we want to store the information and if we don't want to change the inputs. So now I'm going to give the clock 1 and S0 and R1. So as you can see, when clock is 1, here it comes as 1, and I'll change this, and S comes as 0 and R comes as 1. So 1 0, it's going to be 1. 1 1, it's going to be 0. When the S star and R star is 1 and 0, you can see the output is going to be 0 and 1. I'll give you guys a quick tip. That means whatever the S is having, it stores as the Q. That means output. So if you want to remember these things without going for the logic, you can just keep this in mind. That is, whatever the value that S takes, it takes the Q, not the Q bar. So then I'm going to change this to clock is always 1, because if the clock is 0, we are, the output is not going to be changed. So I'm going to give S1 and R0. So same thing happens. R star becomes 1 and S star becomes 0, and these going to be as the I gave this one 0 and 1. As you can see, sorry. As you can see in here, it comes as 0 and 1. Remember guys, clock is always 1. So next we are going for the memory. So that means 1 and S and R are 0 and 0. I'll assume the output as 0. 0 and 1, and I'll give these both 0 and 0. So it comes as 1 1. As you can see, this is the memory state. So obviously the SR flip-flop is going to memorize what's been in output. So it's going to be again 1 0 and 1. And we can see the invalid state is also going to be there after these are stopped. So that is actually the brief on SR flip-flop. So as you can see, the only change is we have added the clock. So now we are going to talk about the limitation of this SR flip-flop. Give me a second. Sorry guys for the okay, we'll talk about the limitation.
one is race condition. Obviously, it's not something about race. It's about that, as you can see, there is invalid state. That is when the SR latch becomes 0 and 0, it's not used. So it's an invalid state. So when this invalid state comes as the input, so then the output becomes unpredictable. So even the flip-flop can't predict what is happening inside it. So that is what we call race condition, and this actually consumes more power, and also this becomes, because of this, SR flip-flop becomes very complicated. So the other thing is, I will explain invalid states also with this regard to this. Actually, these invalid states are the main disadvantages when it comes to SR flip-flop. So these can't be used to store data actually. This can't be used for counters, but this can be used for some small circuits only. So the other thing is, since these are like not very much of reliable, it's hard to design more complex digital systems, and it makes these all things complicated. So limited scalability because of this complexity. Now, how are we going to overcome this disadvantage? That is D flip-flop. Actually, this also has an invalid state, but we can overcome this up to a certain extent. Now we are going to explain D flip-flop. Before moving on to D flip-flop, as Tarsha said, we have a question for you. So get ready, guys, to answer the question. I hope you all were listening well. So moving on to quiz time. What is an example for the use of SR flip-flops? You have 4 answers: racer, stable oscillator, binary storage register, transition pulse generator. You can raise hands, I guess. Yeah. Yes, Rashini, I think you can answer.
Binary storage register.
Yes, exactly.
Rashini, I don't have your index number. Hold on. I need small update. Don't go for it.
Okay, sir.
Thank you so much for the response, Rashini.
Yeah,
Actually,
hold on. Presenters, hold on.
system.
Presenters, please hold on. I need to update a small sheet. Unless it might miss. So Rashini, 2260 25B, I'm correct or not? Correct.
Yes, sir, correct.
All right, thanks. Right, guys, presenters, you can proceed.
Okay, we'll proceed to D
Excuse me.
flip-flop.
Yeah, excuse me. We'll update the marking scheme a bit more. What we can do is first come, first serve. What about now? I think that makes sense, right? Huh?
Yeah.
That makes sense. So we'll go for no. Now it's for the first time. That's fine. From next question onwards, we'll go for first come, first serve.
First,
Agreed?
okay.
All right.
Yes.
Go ahead.
Okay, D flip-flop. Actually, D flip-flop means data flip-flop. As you can see in this diagram, there is only one input. But as we discussed earlier, there should be both 2 inputs. But this is the reason. Here, D input is given as 1 input for 1 gate. Then you can see the same D input as given to the second NAND gate also. So we are using 1 input for the both gates. This is actually for the this is actually to make the circuit a little bit simple, and also to make this very useful. So we'll move on to the circuit diagram and how this works.
It seems some technical issue. So we'll hold on this presentation for now.
No, no. Give us few seconds. Yeah. Okay. So as you can see, this is the D flip-flop. As I explained, there is only one. As you can see, there is only one. There is only one input, and can you see that there is a gate, that is the NOT gate? That means whatever the input they have given to here, the complement of that input comes as the input for the second gate. So why are we giving the complement of one gate? As you can see, this is the truth table of SR flip-flop. I hope you all can see it. So here, to get the Q output as 0, we have given inputs SR as 0 and 1. As you can see, there is kind of a relationship between S and R, that is when S is 0, R is 1. That means the complement of S is going to be R. So as in the next example also, when we want to store 1 in this flip-flop, we have to give SR as 1 and 0. So can you see that every time the whatever the input in S is the complement, R get the complement of S. That means if S is 1, R is 0. If R is 1, S is 0. That's why we are giving this NOT gate. So when we input 1 here, R for the R it comes as 0. So it will never be 1, 1. So the invalid state will be like terminated for some times. So I'm going to explain you one example here. So as I said, if the clock is low, that means this is the clock. If the clock is low, every time it stores what has been inputted. So output is same if the clock is low. So if we want to change the input, we have to change the clock to the active signal. That means it should be high. So when the clock is high, I'll give D as 1. Then R should be 0. So when 1, 0 is going, output should be 1 here and 0 here. So when we are giving D as 0, that means S would be 0, R would be 1. So we get 0, 1 here. And the invalid set won't come because we get the complement complement of one another each time. So it won't be 1, 1. It won't be 0, 0 also. But as you can see, if we want to store something, we can always keep the clock low. That's how this D flip-flop work. I think you guys can understand because this is like the simplest form. And yeah, we'll move towards limitations. So the limitation, no feedback. What is feedback? Feedback is something we are getting from one side to another side. Here, that as you can see, there is no feedback path from the output to the inputs. So output does not affect the input. Sometimes this can be a little bit of a some kind of a disadvantage when it comes to multiplication and division. So the other thing is not toggling. Toggling means every time the output remains constant until the active clock signal activates. What happens if the clock signal or the clock that is broken, then the inputs won't change and the flip-flop won't work. So we are slowly rely on the clock. So if the clock is broken, nothing is going to work. So this happens to be a disadvantage. And the other thing is propagation delay. That means you can see, we change D. We got only one input, and that input comes to the second gate also after inverting to its complement. So there can be a delay because one input can it can take more time to invert one input to another. So, and also it takes longer time for the output to be changed corresponding to the input signal. So that is also a disadvantage. Other thing is, just because this is a simple circuit, it doesn't mean that it's less complex. So when we are designing large circuits and large motherboards, the circuit can be more complex and prone to errors. So these are the limitations of this D flip-flop. Unfortunately, we have to bear these limitations and use the D flip-flop for some of the some of circuits. So moving on, we are going to JK flip-flop. Before that, I forgot, we have the quiz. So we are moving to the quiz, which is actually very easy. So we can see who can answer. Okay, participants 38. That was the first thing. No, Gayasha. Yes, I'm real sorry, I didn't see it. Yeah, you can answer.
Last one is the answer.
Yes. Quiz was which of the following is correct for gated D flip-flop? Yes. Q output follows the input D when the enable is high. Yes. Thank you, Gayasha, for your response. We appreciate it.
Excuse me, Gayasha, what's your index number? Oh, your name in the system. I can't see Gayasha as it is. KJP, Gayasha.
Yes, sir.
Oh, right. Thank you. 226038R.
Yes, sir.
Right. Thank you. Right. Go ahead.
Okay. Thank you. We are moving on to the DK flip-flop. This is actually the improved version of SR flip-flop. Actually, now here we are going to eliminate that no feedback at a disadvantage. At the same time, we are eliminating the invalid state. So this is a bit of complicated because the Q by complement of Q is taken as the input as one gate, and there are 3 inputs altogether. So it's a little bit complex, but let's work this out. So here you can see this is the HR latch. This is the SR latch. Here only we have done a little bit of changes. So again, when the clock pulse is 0, whatever stored in here is going to be saved. So we are going to start it from when the clock is 1. So remember, guys, the clock is always 1. Now I'm going to assume the output we have before the clock is 1 is 0 and 1. So first I'm going to give so since we are going to use 3 inputs, we are not naming them as SR, we are naming them as J and K. So that is a difference between the previously discussed flip-flops and this one. So now we are going to give J 1 and K 0. So 1 1 and this input is going to be here, and this input this output is going to be an input of this one. Yeah. So whatever stored in Q bar is going to here. So clock is 1, J is 1, Q bar is 1. So obviously the output is going to be here. It changes to 1, and here it changes to 0. So I'm going to change the input here then, J and K, keeping the output same. That would be J0, K1. So when passing through the when passing through the NAND gains, you can see that this becomes 0 and 1. So this becomes 0 and 1. Now I'm going to give you the explanation for why we say that this eliminates the invalid state. So I'm going to give J1 also K1. So this is going to be 0. Here the clock is going to be 1. So whenever the flip-flop, whenever the NAND gate is there, any 0, if the input is any 0, then it's going to be 1. So here, this 0 is going to be 0. Yeah, this is going to be 1, and 1 and 0 is there. It's also going to change this to 1 and 0. So it never comes as 1, 1 because we are giving a feedback path. So it never comes as the invalid state. So now we are going to discuss the limitation of JK flip-flop, even though this is the improved version of SR flip-flop. So limitation of JK flip-flop. First one, complexity. As you all can see, we have to get one output. We have to get one output as the input of other. So input. So it's going to be a little bit complex when understanding and when designing circuits. The other thing is power consumption. Since we are using some additional gates and also some additional inputs, it's going to consume more power to power up these circuits. The other thing is propagation delay. The same thing I explained earlier, that it takes long time for the output to be changed corresponding to the input signal. And also limited scalability. This is going to be a common problem for all of the flip-flop because one flip-flop stores only 1 bit. So when we are going to design a very large circuits, it's going to be like really, really hard and complex also. So now moving on to the question. So this is the question: in which condition in JK flip-flop the state does not change? We'll go for answers. Okay, Tanurda, you can answer.
The first one, J equals 0 and K equals 0.
Yes, thank you for the response. Thank you for the response. Yes, this is the answer. So do you need time to get the?
Yeah, it's double 226087. I'm correct, Tanurda?
Yes,
I'm
sir.
correct. Sorry.
Yes, sir. It's correct.
All right. Thank you.
Okay. Thank you for the response again. So moving on to the last flip-flop. Actually, this is not kind of a improved version, but we can use it for some applications also. So we'll go T flip-flop. Last time we discussed about D flip-flop, that is data flip-flop. This is T flip-flop, that is toggle flip-flop. This is kind of a this is kind of an improvement in D flip-flop because in D flip-flop we can't toggle, but here we can do that. So this is also a little bit complicated, as you can see. 2 AND gates are used here. 2 AND gates, not NAND gates, then AND gates, and 2 NOR gates are used. Previously, we used for all flip-flops NAND gates. That is because actually NAND gate is very costly, less costly than the NOR gates. But here we have used NOR gates. So we'll move on. Let's see how this works. So as you can see, if the clock as you can see, if the clock is 0, always it is going to store what has been stored before. So if the t is 1, so t is 0, then here you can see, here we can give these input as j and k, then j and k becomes 0 and 0. As you can remember from the previous truth table, if the jk is 0, it's going to be the memory. So in T flip-flop, there is going to be only there is going to be only three states, that is clock is 0, and when clock is 0, none of the inputs can be changed, and the other thing is clock is 1 and 1, t is going to be changed for 0 and 1. So as you can see, when j and k is 0, it's going to store whatever the previous state has been resolved. So the next input is t as 1. When t is 1, it's going to toggle the input and give the j as 1 and 0. Then it comes as, here comes as 0 and 1. And then the moment it changes to these states, then this output comes to this input and it changes the inputs again as 0 and 1. That is what we call toggling. That means we change the inputs like without giving a chance. We change the input like very fast. That is the simple meaning of toggling. So then it changes to 0 and 1. Then again it changes to 1 and 0, because we get these outputs as an input in here. So I hope you guys can understand what I meant. Actually flip-flop. Now we are moving on to the question. Actually, this is not hard as the flip-flop. The question, we'll move on. Before, I'll tell you the limitation. Inverted output. Actually, here you can see we took one output as the input of other. So this can take some kind of time. So this is an advantage. And limited functionality. That is because it is like cannot be used for multiplication and division, because only one input is used here. The other inputs are output of the previous states, and there can be glitches, like it can produce noise and output can be unpredictable. And also the same, like I said, the propagation delay that is common for all the flip-flops. That means it takes some time for the output to be changed corresponding to the input. So those are the limitations. Unfortunately, we have to face them. That is the technology. So here, and we are having a quiz time. So let's see who is going to answer. Yes, Mihan, you can give your answer.
The fourth answer, which is 1.
Yes, exactly. Thank you for the response.
Go ahead. Yeah, I have noted.
Yes, that is 1. Thank you for your response, Mihan. We appreciate it. So as you all saw, there are some limitations, disadvantages, and actually technicians and scientists are still developing some kind of circuits that are going to reduce this limitation and make them stop. So I think they will be succeeded in future. So I'm going to explain some of the future trends and development. Tarsha is going to explain some of the future trends and development. Yes, over to you, Tarsha.
Right. So we will be covering the recent advancements, integrations with new emerging technologies, potential impacts on digital systems under the future trends and developments. So moving on. As you guys know, most hardware is based on Von Neumann architecture. So a previous team a few weeks earlier did the von Neumann architecture. So I think you guys are familiar with it. So nowadays, scientists are trying to make a new approach. So they are trying the non-von Neumann architecture. This new approach is known as the non-von Neumann architecture. So there have been several solutions. So we are going to talk about quantum computing and neuromorphic computing. And we are going to talk about these two specifically because these two they have the theories of the flip-flops. So they use the same theories as the normal computer flip-flops. So moving on, quantum computing. So basically, quantum computing refers to combining the elegant quantum properties of atoms using electric signals, just as those used in ordinary computer chips. So in quantum computing, there's this something called flip-flop qubit. So as you guys know, the smallest measure of unit in normal computing is the bit. So likewise, in quantum computing, the smallest measure is the qubit. So there's a specific qubit named as flip-flop qubit. It is named the flip-flop qubit because it has the same theory of the normal flip-flops. This is an image of flip-flops or qubits flip-flop qubits used in quantum computing. So neuromorphic computing. So when we say neuromorphic, I'm pretty sure you guys are thinking about the brain. What pops into our mind is the brain and the neurons. So that is right. So this neuromorphic computing is a brain-inspired computing. So the thing is, it has not been commercialized yet. It is still under testing. So, but it will be commercialized sooner. So this neuromorphic computing works like the human brain. So every single neuron sends a signal when the electrical states are changed. So these neurons are the logic gates of these neuromorphic computing. So in logic gates, when the inputs, then when the electric states are changed, it sends a signal. So in neuromorphic computing, when the electric states are changed, these neurons sends a signal. So neurons can be connected to form flip-flops. So in normal computing, logic gates are connected to form flip-flops. So in neuromorphic computing, neurons are connected like logic gates to form flip-flops. So neurons can operate as functionally complete logic gates. As I said, so neurons are the logic gates. Basically, neurons are the logic gates of neuromorphic computing. So we have come to the end of our presentation. So we talked about theoretical aspects, technical aspects, how the flip-flops work, their limitations, and also Oneli, I will hand over the presentation to Oneli. Oneli will give you guys a small recap of what we have done so far. So over to you, Oneli.
Okay, guys, y'all were an amazing audience. Y'all were so attentive and y'all gave quick quick answers. So we started off with what are flip-flops. So we talked about the latches. It was evolved from latches, like flip-flop was the updated version of latches. And then we talked about the differences between the latches and the flip-flops. We talked about the SR latches in the NAND gate, NOR gates, together with their circuit diagrams and the truth tables. Then we talked about the 4 different types of flip-flops according to their inputs and how they change the states. The SR flip-flop, DET, JK flip-flop. And also we talked about limitations of each and every flip-flop. And also we talked about the applications that they are applying, how it is applied to the real world situations, and also the new trends such as neuromorphic computing and quantum computing. So that's all for today. So I hope you guys got a rough idea about what flip-flops are and how it works, the truth tables and stuff. So unfortunately, we could have done much more better if it was physical, because it's quite a hard topic to explain online. But however, we think that we did a great job. And finally, do y'all have any sort of questions? It's the question time. Any questions?
All right. It seems no questions, guys. For me, content-wise, I'm really appreciate you. You have done up to good level of thing, but I feel the presentation is not up to the UM standards. I'm sorry to say, presentation skills are a bit lower than the other teams that up to come this extent. I don't know what the reason behind is. You people are laughing to the camera for some reason. It makes drastic impact on your marks. I'm really sorry to say. Other teams, please don't do this mistake again. It happens to one team, not let happen to your teams, which makes drastic impact, guys. You know, it's 20 percentage now your presentation marks, and it's 10 percentage altogether the presentation skills. So please be careful when you are coming front to the audience. Your behavior, your actions, your uh, feelings to the environment might be not up to the standards that we are expecting. That might impact for you in future for your monetary things, for your money. Today it's points or marks, which can be manageable, but in future it might be money. So please be careful whenever you come to front. Right? Thanks, team. I'm really appreciated your effort. It's a good work that you have done. You have gone through much more theory work. It's good. Theoretically, you have explained a lot. Right. So we'll see if guys, if you want, you can go for a small discussion in next week, because this is a complex topic. I would strongly encourage everyone to go again with these slides and other stuff. Further, if there's any possibility, we'll give this around team around 10 minutes to 15, just 10 minutes around a small recap on what we have, what you people have done. That might be really important for the entire students. All right, thanks. What's your name? Harini, I can't remember.
Oneli, sir. Thank you.
Oneli. Yeah, Oneli. Oneli and team, thank you. For some reason, I don't know, I got from mail only from Tarusha. You haven't copied for some reason. Again, it's you know, teamwork wise, you are getting a bit lower marks in that corner also. So which makes be careful in future, whatever you are doing. Right. All right, thanks. Your effort is appreciated. You came to a place, physical place, and spend thousands and come to this place, and it's a good job. We appreciate that effort.
Thank you, sir. Sorry for the mistake.
No worries, no worries. Mistakes are common for the first year students. You can fix in future. You will get pain once it comes to marks. That pain will fix you a smile easily, right? Okay, thanks.
Yes, sir.
All right, good. We'll go to the next team.
Sir, we are having another two individual presentations.
Sure, Mihan and who is that?
Mihan and Rashini.
Mihan and Rashini, go ahead. Mihan, your presentation is very small, I think. Any possibility to expand a bit more? Mihan?
Sir, I thought you were supposed to do about 5 to 7 minute presentations, so I made
All
it
right, all
small.
right. All right, nice, nice. That's all right. I just want to check whether you have updated a bit more or not. Okay, nice. Yes, go ahead. Who is this? Rashini. Yeah, Rashini, go ahead.
I added a bit more to the explanation, sir.
Yeah, sure, man. That's fine. It's totally okay. Yeah, Rashini, go ahead.
Can you hear me? Hello.
Yeah, Rashmi, go ahead.
Good afternoon, everyone. Today I'm going to present about parallelism. What is this parallelism? Parallelism is executing multiple tasks simultaneously. And what does this simultaneous mean? Like, you get to hear simultaneous in different occasions, like in ICT and mathematics, and some of you may not even know what simultaneous means. Let's see what simultaneous means. In mathematics, we have something called simultaneous equations. Here I have included the simultaneous equations, and here I have included a woman. Why would I include a woman in a presentation and for the meaning of simultaneous? You can take your mother for an example, like she can be going to work and doing housework and office work, everything at the same time. That is what you call simultaneous, doing something at the same time. So I think now you have an idea of what simultaneous means. Therefore, parallelism means doing tasks at the same time, simultaneously. When talking about parallelism, it is important to know what serial computing. Serial computing is the opposite of parallel computing. Let's see what serial computing is. In serial computing, one problem is broken into discrete series of instructions. So those instructions are executed sequentially after one another through a single processor. That's the main point in serial computing. There is only one processor and only one instruction is executed at a time. You see there is instruction T1, and after instruction T1 being executed through the single processor, then the T2 instruction is get executed. And then here comes parallel computing, which is our topic. In parallel computing also, there's the problem, and this problem is broken into discrete parts. In serial computing, the problem is broken down into instruction, and here the problem is broken down into discrete parts, and each part is broken down into instructions. So when each part is further broken down into a series of instructions, those instructions are executed on different processors. You can see there are 4 processors, and one part of the problem is executed through processor 1, another part is processor 2, and likewise, in multiple processors, the parts of the problem is executed. So there is a coordination between those processors. Let's see what are the types of parallelism. There are 4 types of parallelism when you search on the internet, like data parallelism, task parallelism, instruction level parallelism, and bit level parallelism. But for our syllabus, as in for operating system concepts 9th edition, we only have 2 types of parallelism, which is data parallelism and task parallelism. So let's talk about what this data parallelism and task parallelism is. Parallelism. It is the concurrent execution of the same task on each multiple computing core. I know you didn't got what I just told. Just remember the keyword is same operation. You just need to remember same operation, and I will explain what is data parallelism through an example. Consider, for example, summing the content of an array. Here, this is the array. The size of the array, which means the size means n, is 10. On a single core system, here there is only core 0. One thread would simply sum the elements from 0th index to n-1 index, which means from index 0 to the 9 index, it will just simply add all the elements in the array. So it's just 10 plus, 50 plus, 30 plus, 10 plus, 20 plus. Likewise, it will just add up all the array at the like from one core. But on a dual core system, however, thread A you can see running on core 0, and it sums up the elements from 0th index to 4th index, which means this is this single array is divided into two parts, and one part is executed on core 0, and the other part is executed in core 1. So here there is dual core system, and you have heard probably like quad core system. Like there can be different amount of cores. If there are 4 cores in this system, this array will be divided into 4 parts and then executed separately on different cores. So that is what you call data parallelism. The single task is divided into different parts and executed in different cores. So it's just the same operation that is executed in different cores. Contrast, task parallelism is the concurrent execution of different tasks on multiple computing cores, which means unique operation. In data parallelism, you saw there are the single task is divided into 2 parts and then it was run in 2 cores. But in task parallelism, in each core, there are different tasks running. For example, in core 0, there's a task called sum up the array. There's an array and you have to sum up the array in core 0. And in core 1, there is another task that you have given. Find the odd numbers of the array. So there are 2 different tasks and unique tasks are run on the different processors. So I think now you can understand what task parallelism and data parallelism is. So to sum up, in data parallelism, distribution of data across multiple cores. So the data in the same operation is distributed among multiple cores. Contrast to that, in task parallelism, there are unique tasks across multiple cores. So parallelism is not a huge topic. That's the end of my presentation. Are there any questions? If there are no any questions.
Thank you. Yeah, thank you, Rashini. Parallelism is a big topic. You know, it's a big topic once it comes to MSc in computer science. It's a complete subject. You know, it's a very detailed subject. It's very long, very lengthy, and it's very detailed topic, right? Somehow, good. Thank you. For a first year student, it's more than enough. And good that you have gone through the reference book and you understood the scope. Good. Appreciate. All right, we'll go to Mihan.
Let me know if my screen is not clear or if I'm getting laggy.
Sorry?
Can you let me know if my screen is not clear or if I'm getting laggy while I'm presenting?
Sure, definitely, Mihan.
Thank you.
Rashini, you can leave.
Yeah, sir.
No
I'm
need to
connected
leave.
from 2 devices. Like
2 devices. Right, Mihan, go ahead.
Okay. So guys, when you're studying or doing assignments at home, you usually keep the things you need near you, right? For example, instead of going to the bookshelf back and forth every time you need to refer to a specific set of books, you can keep those books on your desk where all the work is done. But your desk doesn't have a lot of space, unlike the bookshelf. So you only keep the books you really need near you. This is a real-world example of what is known as caching. 1 second. Good evening, everyone. I'm Mihan Tilagaratna, here to present about caching. Technically, caching refers to the process of temporarily storing frequently accessed data in a faster storage system, which is the cache. When we need information, the processor first checks the cache whether it contains that piece of information. If it does, it is known as a cache hit, and we use that information. If it doesn't, it's known as a cache miss, and we move on to the main source of information, which is usually the main memory, and keep a copy of that information in the cache in case we need it in the future. The cache memory usually stores data temporarily. It is located on or near the CPU in order to reduce access time and to increase speed. Therefore, the cache memory is small and fast. It uses SRAM or static RAM, which uses flip-flops, which were brilliantly discussed in the presentation before us, and in order to store data, and is known for its fast access time as opposed to the DRAM or dynamic RAM. SRAM stores data as long as power is constantly supplied, and it doesn't have to refresh to remember the data. Caching systems utilize the principle of locality, also known as locality of reference, to improve performance. Principle of locality refers to the tendency of the processor to access the same set of data clusters within a short period of time. It includes temporal locality and spatial locality, which I will discuss in order to explain this topic further. Temporal locality refers to the tendency to reuse the same set of data within a small period. Take the bookshelf example. If we have to refer to a specific book again and again, it would be much easier if we kept that book on the tiny desk instead of going back to the bookshelf every time we have to refer it. Next, we have spatial locality. Back to the bookshelf example. Imagine that each shelf was arranged according to some order. For example, the book we just referred to might be about microeconomics, but the book next to it might be about macroeconomics, and there's a high probability that we might have to refer to that book as well. In other words, there's a high tendency to refer to the data stored near the data we recently accessed. Temporal locality is related to time, while spatial locality is related to relative location or space. Next, we will look at the levels of cache. There are mainly 3 levels of cache, namely level 1, 2, and 3. Level 1 cache, also known as the primary cache, is usually embedded onto the processor's core and is the fastest out of the 3 with the smallest capacity. Level 2 cache, also known as the secondary cache, can either be embedded onto the core or can be outside the core as well. It is lower than level 1 cache but has a higher capacity. Level 3 cache, also known as the external cache, is usually stored in a separate area known as the off core or the uncore, or it can even be located in a separate chip known as the chiplet. It is lower than the other 2 levels, but it has the highest capacity. It improves the performance of the other 2 levels when the processor of the other 2 levels. When the processor is searching for data, it first checks the level 1 cache for whether it checks the level 1 cache for whether that data is available in it. If it isn't, then it moves on to level 2 cache and then to level 3 cache. Next, we look at cache coherency, which is related to computer systems with multiple processors. It refers to the uniformity of shared data stored in multiple local caches. Basically, what that means is that when the same data is stored in several different caches, the data should not be different from one cache to another. This will be clearer when we look at the cache coherency problem, which I will explain now. Imagine we have the integer a, which is copied on several caches, P1, P2, and P3. Because this is a multiprocessor environment, we can run several processors at once. So in P1, we won't change the value of the integer, but in P2, we will deduct 1, and in P3, we will add 2. So finally, the same data point will take 3 different values as 3, 2, and 5 in 3 different caches. The shared integer is not uniform and is not synchronized. This is known as the cache coherency problem. Next, we have the cache replacement policy, which determines how data is replaced when the cache is full and new data has to be written. There are many different methods, some of which are listed in this slide. I won't be explaining them individually as the names are pretty self-explaining. Next, we look at the cache write policies, which refers to how write operations are handled in a cache system. It determines how and when the data is written in the cache. First, we have write through, where both the cache and the main memory are updated at the same time whenever a change is made. This minimizes data loss, but is time consuming. It ensures that the main memory and cache are consistent. Next, we have write back, where only the cache is updated when a change occurs. The main memory is updated only at intervals. This reduces memory traffic because multiple writes are combined into one single write when updating the main memory, but it has a risk of data inconsistency between the cache and the main memory. This brings me to the end of my presentation about caching, which included an introduction about caching, the principle of locality, levels of caching, cache coherency, cache replacement policies, and cache write policies. Thank you and have a great day.
Thank you, Mihan. Any questions, guys? Caching? All good? Quickly check your cache levels L1, L2, and L3 caches and drop me an email, guys. Take a screenshot of your L1, L2, L3 caches and send it to me. I will add 10 points for that screenshot. Sizes of L1, L2, L3 caches. All right, I think guys, can you hear me? Yeah, it's more than enough time to submit or send the screenshot of your L1, L2, L3 caches. And I have received few and good, thank you. And I will appreciate by adding points to your profiles today itself and good. Any other presenters today?
No, sir, that's all for today.
That's
Sir,
all.
Sir, regarding the flip-flop presentation,
Yes.
personally, I don't think it's fair to reduce that many marks because their whiteboard fell. So there were some problems, but I don't think it's really worth losing that many points, considering their appearance and that they were on time and ready, and we really understood the presentation and
Really?
they had thoroughly planned it, and it was really well done overall, sir.
But not for me. Thanks, Mihan, for your effort. All right. Well, any other questions, guys, for today? Mihan, you know, once I'm an engineer. We went 5 minutes later for client's meeting. You know what was happened? The client escalated to vice president. It was gone through like everywhere. Right, 5 minutes later. Small mistake. I have worked for top-notch client in the world, right? Time back. They was really aggressive. This kind of a laughing people might get into a big trouble at the end of the day, you know. That's there should be some learned lesson for them. I'm not cruel. I'm not hate among any student. You all are same for even island first to island last. Anyone comes to my class, any CEO or directors, I'm teaching to directors. I'm teaching to vice presidents. I'm teaching to top-notch people in industry. Right? Whoever comes to my class, it's a student. That's it. So it's all responsibility of a student to present well, not to laugh. Content quality, network quality is not a problem at all for me. I don't care. Right? I have given opportunity for one team to do it next class, isn't it? That's not a big deal. I can understand. I'm very empathical. Most probably it's beyond the empathical. Sympathy is more than. But this kind of a situation, these students like entire team should learn a lesson. It's a lesson for life. One day it's money. Today points, today marks converts to money in future. They'll learn it today, then they'll fix. Don't get upset. I don't care about these whiteboards issues or network issues or any other thing. That's totally okay for me. And I'm not get upset with those kind of network issues and stuff. I know because I'm doing online lessons from time back, starting from COVID onwards. And I have this experience where. Right. Thank you. Anything else to discuss, guys? No, all good. Right, then we'll meet next week physically. This lots of students, if I'm not mistaken, send your PowerPoint presentations. Sorry, I haven't uploaded it yet, but I'll upload it definitely next couple of days and finalize all the things. So that's all for today then. Have a nice day. Make sure to add your attendance details. Who is this? Representatives. Please check whether they are completed the attendance sheet properly or not. If there's some issues, let me know. Yes, Ajana?
We have already taken pictures of the participants.
Good. And there is Excel sheet that I have shared with you.
All right, so I'll look into that as well.
Sure. Now, last week I have shared an Excel sheet, so you can add the details to the same sheet. Probably, I think you have access. If not, let me know.
All right, so okay.
Let me know. Somehow, if Sajjana, right?
Yes.
Sajjana can manage the attendance, that's all. For me, that's totally okay whether you are attending or not, because I have just take a couple of times. I know the people who attended or not. So it's up to you to decide. Guys, thank you.
We both will look into it, sir. Yeah.
Sorry?
We both will look into it, sir. No worries.
Good. Thanks. You are doing a good job, Sajjana. And the other one's name is, what's your name, dear?
Ashane, sir.
Ashane. I can't remember for some reason. Ashane,
Sir,
thanks.
I uploaded those videos to the Google Drive and I sent the link.
Please share it. Then we'll finalize everything and complete this work, because the people who don't have experience, then they can go through your presentations and stuff. I'm not asking any question out of these presentations, guys. Or everything asking inside this content that you have presented to your teams, right? I'm not asking any single question out of these presentations and presentation slides. Except what we call logical gates. Logical gate question is quite open. The other stuff, it's inside the scope that you have discussed in the class, because you have almost gone through the boundaries. I really appreciate everyone's presentation up to now. It's like content wise superb. No word for that. Everyone's content is like extremely nice. I really appreciate everyone's content up to now. All the presentations are good except small issues. Right, guys. Then we'll meet next week. Then, as usual in the physically. If there's any update, Ashan and Sajjana, please let me know earliest as possible.
Okay, sir. Sure.
Okay.
All right then. Bye. Have a nice day.
Thank you, sir.
Thank you, sir.